In this video, we're going to learn about a new addition reaction to alkenes called hydroboration. Now, if you recall, we've already looked at two main reactions of alkenes. One is the addition of a hydrogen halide across a double bond, which is called hydrohalogenation, and then one in which you add water across a double bond, which is called hydration. And we see that if we use an asymmetric alkene, so for example, one in which there's on one of the olefin carbons there's an R group or maybe two R groups, and on the other olefin carbon there might be two hydrogens, right? So if I treat this with HBr, I know where the hydrogen adds and I know where the bromine adds. So the hydrogen adds to the carbon with the most number of hydrogens, and the bromine adds to the carbon that is most substituted. Now, we know why this happens because you form a carbocation, so the more stable carbocation is going to be the most substituted carbocation, and then bromide attacks that carbocation. So we know this mechanism, or we should know this mechanism pretty well. Now, we've also seen in the hydration that this similar asymmetric alkene can react with water in the presence of an acid. So we get proton transfer, and again, forming a carbocation, water attacks that carbocation and then gets deprotonated. So the end result is we form an alcohol, and that the OH group adds to the most substituted carbon. The hydrogen adds to the carbon with the most number of hydrogens, in other words. And so we call this type of addition Markovnikov addition, and Markovnikov's rule simply states that the hydrogen goes to the carbon with the most number of hydrogens, or the alcohol goes to the carbon that's most substituted, or the bromine goes to the carbon that's most substituted. So there are little variations of the rule, but in essence, Markovnikov simply discovered that in all addition reactions to alkenes with HBr or with water, the hydrogen always goes to the carbon with the most number of hydrogens. So we call this Markovnikov addition. Now, we know why that is the case, and so we typically don't necessarily go by the rules, but when you're trying to categorize a whole bunch of reactions, which we're going to be doing in the later chapter, we're going to see that sometimes it kind of helps to think about rules in place, but then to understand how those rules, why we actually abide by those rules. So we know that in both of these reactions, the alkene is behaving as a Lewis base. It donates a pair of electrons to an electrophile. So the pi bond will react with Lewis acids. And the Lewis acids that we've seen so far are also happen to be Bronsted acids in that they donate a proton. But remember, a Lewis acid is something that simply accepts electrons. So HBr is going to accept the electrons, the pi electrons, and you get proton transfer. An acid accepts the protons, accepts electrons, and you get proton transfer. So both of those reactions are proton transfers, but it is simply a nucleophile reacting with an electrophile, a Lewis base in the pi electrons reacting with a Lewis acid. So we can think about other Lewis acids that a pi electrons can react with. And one such reaction is what we call hydroboration. Now, hydroboration is where you take an alkene and you react it with borane. So borane, which is BH3, is a Lewis acid. And if we look at the structure of borane, we see that it is a trigonal pyramidal molecule. So We know that the boron happens to be sp2 hybridized, and since it's sp2 hybridized, then it has an empty p orbital. And so we can think about that empty p orbital, and we know that we've seen lots of reactions in which the HOMO pi carbon-carbon pi electrons donates to empty p orbitals. And that's exactly what's going to happen here. And as a matter of fact, borane is such a good Lewis acid that it often complexes with solvent that it's in. So if there's any lone pair of electrons on that solvent, those lone pair of electrons can donate, act as a Lewis base, and donate to the Lewis acid of borane. One of the solvents that we often use is called THF. So tetrahydrofuran, THF, we know this solvent well. It's a cyclic ether. And if we take borane with its empty p orbital and we react it with THF, and you see the lone pair of electrons on THF, right? So here we have THF. Those lone pair of electrons can donate into that empty p orbital. And the result is that you get what's called the BH3, a borane THF complex. And of course that stabilizes borane so that it can actually be transported. So oftentimes if we don't use a solvent like THF, or diethyl ether even works fairly well, then borane tends to dimerize on itself. So that's something that we need to recognize, that you have this BH3 THF complex, but in reality, in solution, that is a fairly weak interaction because you're developing a charged species that's taking place there. Now, why is this important to us? Well, we can take an alkene and we can react it with BH3. So it's going to be in THF. We typically don't think of it existing, when we draw the mechanism as that BH3 THF complex. We think of it simply as a free borane. And what happens is you get borane to add across the double bond, and so you get a hydrogen to add to one carbon and a BH2 to add to the other carbon. And this is called an alkyl borane. Now, how does this take place? Well, the mechanism is a little bit more complex than the addition reactions that we've seen already, where you form a carbocation and then a nucleophile attacks that carbocation. So if we think about the possibilities, the possible mechanisms that can take place, one possibility is very similar to what we've seen already, right? We take the alkene, we react it with a Lewis acid, so borane is the Lewis acid, the alkene is the Lewis base, the HOMO is the pi electrons in that carbon-carbon bond, and it donates to the LUMO, which is the empty p orbital of the boron, so boron p orbital. And so we get this, and we again would form a carbocation just like we've seen before. Now this is called a hydroboride because now the boron has a negative charge. And so what could possibly take place? Well, we could possibly get a hydride to donate to the carbocation, and that's how we would get our product. So notice hydrogen goes to one side, BH2 goes to the other side. But also notice in this kind of context, you're not adding a proton, you're adding a hydride. So that is a possible mechanism, and certainly it would be similar to the two other addition reactions that we've seen, right? Where you're donating the pi electrons to an electrophile, forming a carbocation, and then a nucleophile attacks that carbocation. So that would make it easy, but it's not quite so easy, and the reason is because there are no rearrangements during hydroboration. So what does this mean? Well, if we know there are no rearrangements during hydroboration, then that means that there cannot be a carbocation. So regardless of uh, any beta carbons, there is no carbocation. So we cannot be forming a carbocation in this reaction pathway. Well, so we have to think of another possibility. And one other possibility is if the alkene reacts with the borane in a concerted mechanism, so that the pi electrons donate to the boron, and then a hydride adds back to the carbon kind of at the same time. So this is a concerted mechanism. It's a little bit different. And what you form is this, you form an intermediate that is a four-membered ring, right? So the pi electrons are starting to form a bond with boron. The boron hydrogen bond is starting to break, and the electrons are starting to form a bond between hydrogen and carbon until eventually you get our alkyl borane. And in this type of mechanism, this type of concerted mechanism, you see that there's no carbocation that is formed. So this is more consistent with the results that we see where you get absolutely no rearrangement. Now, there is regiospecificity in this reaction. So just like we've seen with the addition of HBr and water, there's regiospecificity in that the nucleophile always adds to the carbon that's most substituted. If I take an unsymmetrical alkene and I react it with borane, I always get this. So the hydrogen adds to the carbon that's most substituted, and the BH2 adds to the carbon that's least substituted. Now notice it's kind of a reverse. So, we typically say the proton adds to the carbon that has the most number of hydrogens. But in this case, the hydrogen is not a proton, it's a hydride. It has hydride type characteristics. So we always want to say, well, why is this the case? So let's take a little bit closer look at what's going on here. We know that we have our pi electrons that are being donated to the borane. So I'm going to draw borane down here, and I'm going to draw its empty p orbital. And so what's happening? So we start to get donation and to that empty p orbital, and now and of course the electrons from one of the boron hydrogen bonds, it starts to donate its electron density to one of the carbons. So what's going on here? Well, we see that upon bond formation, one of the carbons is going to start to take on a partial positive charge. It's going to be the carbon that is most substituted. And that carbon there is a tertiary carbon. The other carbon would be a primary carbon, and therefore a tertiary carbon can build up a partial positive charge. Just like we saw with carbocation formation. Obviously, we're not forming a carbocation here, but we are forming a partial positive charge on one of the carbons, and certainly a tertiary carbon can do that much easier than a primary carbon can, right? The energy would be much lower in this transition state. And so this leads to now the boron BH2 adding to the least substituted carbon, and a hydride adding to the most substituted carbon. And this is the only observed product we always get, right? And so this must be how we explain the regiospecificity occurs this way. Now, the other thing that we can think about is if this concerted mechanism is taking place, then we should have some stereospecificity. Because if you look here, in order for all this to happen, the BH2 and the hydride have to add kind of on the same side as one another, right? So if we think about stereospecificity, we see that this reaction indeed proceeds in what's called a Syn addition. So Syn addition is simply when the two groups add to the same side. So Syn addition is same side, right? And we can demonstrate that by taking an alkene like this, right, where you have two deuteriums on, and you react it with some, you know, dialkyl borane species, and you get this. And so this is the only um, stereochemistry of this reaction. Now, obviously, you can add it to the top or you can add it to the bottom. So you end up getting the enantiomer of this as well. You get a racemic mixture of the two stereoisomers of one another. So there's stereospecificity. The hydrogen and the borane add on the same side. And so this plays out particularly well in cyclic alkenes, right? So here I have 1-methyl cyclopentene, excuse me, and if I react this with BH3 in THF, I get the addition of H and BH2 across that double bond. They add to the same side, so obviously I would get the enantiomer of this as well. But the key is that the hydrogen and the BH2 are adding on the same side. So it's Syn addition. Hydrogen and BH2 are on the same side. So that's important to recognize as well. So we have regiochemistry, where the BH2 adds to the least substituted carbon and the hydride adds to the most substituted carbon. And we also have stereospecificity, in which both the hydride and BH2 are adding on the same side as one another. Now, a little bit to complicate things just a little bit more, there is a possibility of multiple hydroborations. So what do I mean by that? Well, if I take an alkene and I react it with borane, right? So I get addition across the double bond, and the hydrogen adds to the more substituted carbon, the BH2 adds to the least substituted carbon. But notice I still have an alkyl borane. So the boron is still a Lewis acid, and it can react again with another alkene. So I can take this and I can react it with another alkene, and I end up getting dialkyl boron. And of course, there's still, this dialkyl boron is still a Lewis acid, and so it can react with another equivalent of an alkene, and I get this. So this is what we refer to as a trialkyl borane. And now, of course, there's no more hydrogens, so you can't get any more addition of hydride, and the reaction can stop there. So oftentimes, when we react an alkene with borane, you can get multiple hydroborations to occur. And obviously the degree of substitution simply depends on steric effects. And in practice, it's kind of difficult to predict how many hydroborations you're going to get. This is oftentimes why we use not just borane itself, but some already alkylated borane. So maybe a dialkylated borane. If you use a dialkylated borane and react it with an alkene, then obviously you can only get one hydroboration to occur, because now you've formed a trialkyl borane. So sometimes it's kind of easy to predict. So if I have 1-butene and I react it with BH3, there's no steric effects. I'm going to obviously get addition 3 times, and so I end up with this tributyl borane. But notice if I want to kind of stop that from occurring, I can react it with dimethyl borane. I can react butene with dimethyl borane, and of course I'm only going to get one hydroboration here, and so I get butyl dimethyl borane. And so, oftentimes we're going to basically assume that you can get multiple hydroborations. But obviously, if we see something like this, that's a tetra-substituted alkene, there's going to be a lot of steric effects here. So even if I took this and reacted it with BH3 and THF, I'm only going to get a monoalkyl borane. So there's all different variations of this type of reaction, but the key is to recognize that you're getting a hydroboration, and sometimes that hydroboration can happen again and again. And so that's something that we have to kind of keep our eye on. But for the most part, in terms of synthetic value, there isn't a whole lot of synthetic value in just making alkyl boranes. We're going to see in the next video that the reason for making alkyl boranes is that from that we can make alcohols.